So let's talk a little bit about bone formation. So I'm going to hide myself here. Basically, all embryonic connective tissue, doesn't matter what type of connective tissue it is going to begin as something called mesenchyme. So essentially, you can kind of think of this as a type of stem cell, right? I mean, it can only give rise to connective tissue. That's the only thing it can become, but it can become any kind of connective tissue, right? So we're gonna hear this term a little bit here. So these, again, embryonic connective tissue begins as something called mesenchyme, and then it'll differentiate into cartilage, into dense connective tissue, into bone, into blood. All right. Anyway, another term for you is that bone formation is called osteogenesis. So when we're talking about osteogenesis, what we're really talking about is you building bone. And really, there's two different ways that our bodies make bone, right, developmentally. Right? We have something called intramembranous ossification, and then we have endochondral ossification. And again, that should be a 2. Intramembranous ossification is they're slightly different. So this is the formation of bone directly from or within fibrous connective tissue membranes. Okay. So again, intramembranous, we're forming it from within or from a connective tissue membrane. All right. Endochondral ossification is slightly different. So we're forming bone from a hyaline cartilage model. Okay. So we actually create cartilage, we make it look like the bone, and then we're going to turn that into bone. Right. This isn't quite the same. It's more from the sort of a connective tissue membrane. So let's take a look at them individually. And I have a link to a YouTube video. You can watch the video if you like up here. So intramembranous ossification, this is going to form flat bones of the skull and then your mandible, so your jaw. Right? This is the basic 4-part process and how it happens. All right. So the very first thing that happens, again, remember what we start with are mesenchymal cells. Right? So we're starting with these cells. And then what ends up happening is that these mesenchymal cells are going to turn into osteoblasts. Right? So mesenchymal cells become osteoblasts, and osteoblasts build bone. So they lay down what's known as an osteoid matrix. So what that means is, instead of calling it bone, because technically it hasn't hardened yet, the calcium hasn't come in yet, however, it will. So it's sort of like a precursor form to it. So we call it an osteoid matrix. Right? So these mesenchymal cells, these undifferentiated cells, they get a signal. So this is all genetically sort of pre-programmed. They get a signal. They specialize. They become osteoblasts, and those osteoblasts start laying down this matrix. Now, the location where that happens, where that starts, we call that an ossification center. Okay, so simply where that's occurring, it's called an ossification center. All right. So then we take that matrix, okay, it ends up surrounding the cell because basically, you have a cell here, let's say this is the cell, and it's producing the stuff around it, right? So here's this bone that it's making, and I'm just drawing it like that. I'm not saying it's creating the concentric lamellae or anything. It's just producing all of this osteoid matrix around it, so it becomes surrounded by it, right? That osteoid matrix then calcifies. And as it calcifies, that osteoblast can't make anymore because it's bone. It can't push it out anymore. It's surrounded by this hard thing. So since it can't make anymore, it matures. It becomes an osteocyte. Okay, so hopefully that's pretty straightforward. So that as this osteoblast is making that osteoid matrix, eventually it calcifies. It basically traps it in that lacunae and in the canaliculi. And then an osteoblast it stops producing the osteoid matrix and simply becomes an osteocyte. Okay. And you may have some forming here. You may have some forming here, right? So you have like all of these different ones forming in different areas. So they form bridges of trabeculae. Okay. And then that makes up spongy bone. And then you have red bone marrow in between these, right? And then on the edges, on the periphery, not only you start laying down compact bone, and that mesenchyme, instead of forming osteoblasts, it ends up forming the periosteum. So again, remember, mesenchymal cells can become any kind of connective tissues on the periphery or on the edges, they end up forming the periosteum. Right? So let's just take a look at what that looks like in image form. So here in this first picture, let me see if I can get my pen here. Come on, pen. All right, I'm having a little bit of trouble trying to get my pen, unfortunately. There you go. All right. So in this first one, you have these. You can see these mesenchymal cells. So here's a mesenchymal cell. Here's one. Here's one. Now these right here, they were mesenchymal cells. However, they differentiated and they became osteoblasts. Okay. And so now they're laying down that osteoid matrix, and the area where this is occurring is called the ossification center. Right. So that osteoid matrix starts to calcify, and we actually start forming bones. And now these cells, since it can't go anywhere, it can't produce anymore, it matures and becomes an osteocyte. And it's trapped itself in that little space, and again, that space is a lacuna. Okay. Around the edges, we still have osteoblasts, and all these other mesenchymal cells can also be differentiating, forming some new osteoblasts. So basically, this growth continues until we have these trabeculae. So you can kind of see here is like a trabeculae, a trabeculae, trabeculae. So these are going to start coming together. Again, still along the periphery, we have some of these osteoblasts. They're building the bone, this way, this way. Okay? And you can see on the outside of those, the mesenchyme is starting to condense. So you can kind of see here, like even in image number 1 up here is kind of loose. Now it's starting to condense by now. So along the very outside, those mesenchymal cells form the periosteum. That spongy bone is only located in the middle. And then along the outside edges, you now have this nice compact bone. And you'll notice you still have some osteoblasts, which is kind of nice and important because, again, your bones are always under stress, so they may have to remodel themselves, or if you break your bone and they have to heal themselves, these osteoblasts are what's going to help heal the bones. Okay. Now, endochondral ossification is going to involve the replacement of cartilage by bone and forms most of the bones of the body. So the last type, the intramembranous ossification, that simply formed bones of the skull and the mandible. Endochondral ossification forms most of the bones of the body. And you can just ignore this figure 6.6. That's from an old textbook. I meant to take that out of this PowerPoint. Okay. The very first step in endochondral ossification is going to be the development of a cartilage model. So if we take a look at this next picture, take a look at this next PowerPoint. So again, it forms basically all the bones except bones of the skull, the mandible, and including your clavicles. Again, you have a little hyaline cartilage model. And you can see it starts about at the second month of development. And then basically until those epiphyseal plates fuse, until your growth plates fuse, endochondral ossification is constantly occurring. Okay? So I know it's a busy picture, so let me try to break it down for you. All right. So what you're looking at here in this light blue, that's going to be the cartilage. So that's a bone. Okay, pick one. Again, we have this hyaline cartilage model. So the very first thing that's going to start happening is that you form what they call a bone collar around the model. So here we have a little bit of a cross section. But what you're seeing here, right around the edges, is this kind of collar that's forming around that hyaline cartilage. Okay. Now, what ends up actually happening is that this cartilage is avascular, okay, meaning that it has no blood vessels. So once you form this bony collar around it, it starts starving off these cells in the middle. Okay. So what ends up happening is that the cartilage in the center, what will become the marrow cavity, starts to deteriorate. And what you're seeing here, again, imagine like a 3D image. What you're seeing there is sort of that other part of that bony collar, so like that back part. So imagine if, like, I don't know, like you put a collar around you, and now what you're seeing is like the back part of it, because now where your throat is, it's hollow, and you're seeing straight through. So that's basically the cartilage matrix is deteriorating. You're forming a cave. It's called cavitation. Okay, that's all it is. So again, bony collar is laid down around the outside. Basically, the cartilage on the inside deteriorates. You have a bone, basically a space starts forming. Now, into that space, a blood vessel is going to make its way. Okay, again, these blood vessels are getting their signaling. They simply form a hole and basically go in. It's a very complex signaling cascade, allowing your body to, direct blood vessels to where they need to be. Okay, once they do that, once you get blood vessels, again, bones are going to be highly active. It's a lot of work. I mean, think of all the material that you have to lay down to make bone. Once this blood vessel comes in here, now we start forming this medullary cavity. So now you start seeing not just the deterioration of cartilage, but now the bone formation forming. Because basically, along with the blood vessel, osteoblasts have also come in, and now they're starting to form bones. Okay. And then what you end up seeing as well is that on the epiphyses, you also have blood vessels coming in. And again, as soon as you have blood vessels coming in, you're going to have bone formation. So basically, in the center here, in this marrow cavity, we call that our primary ossification center, because that middle part is what's going to ossify first. And then in the epiphyses, we'll have what are known as secondary ossification centers, because that's where the next sort of area of bone formation is going to be. Okay. And then basically that continues. So basically, bone continues to grow toward the epiphyses, and then the epiphyses themselves will grow until all that you have left is sort of that area in between the two, right? So you have one at the proximal end, and then you have one on the distal end, okay? And those are our growth plates. And then the last sort of bit of cartilage that remains too is at the very ends, and that becomes our articular cartilage. And if I haven't mentioned this to you before, this term articular simply means a joint. You can kind of think of it that way. So wherever two bones come together, that is called an articulation. So if you have anything articular, it simply means where two bones are coming together. So it's simply like a joint. All right. So let me just kind of run through this one last time, kind of all through. So we have a hyaline cartilage model. It's the way we start. We start forming bone around the outside along the diaphysis, that very small diaphysis at that point. That basically is starving off the cartilage cells in the middle. They deteriorate, we form a little cave, the cavitation. Okay. Blood vessels are going to invade that cave, that little space, and once they do, they take osteoblasts with them. That allows bone cells, the osteoblasts start building bone in that medullary cavity. Similarly, you're going to have blood vessels invade the epiphyses. Along with them come osteoblasts. So now we have what are known as secondary ossification centers. So you start building bone not just from the middle, but from both ends. Where they come together, where the epiphyses and then the diaphysis comes together, you have a little bit of cartilage remaining that is called the epiphyseal plate. That's your growth plate. And then at the very ends of your bones, you'll also have a little bit of cartilage remaining. That's there for the joints to add cushioning and shock absorption and friction reduction. So that's called articular cartilage. So hopefully that makes sense to you. If it doesn't, please feel free to email me, and hopefully I can help you out. All right. So bones are obviously, as we get older, as we mature, we get taller, so, right? So bones are going to grow in length. And again, that's what that epiphyseal plate or growth plate, that's what its role is. What's going on is we have cartilage cells. They're reproducing by mitosis. Okay, and that's occurring on the epiphyseal side of the plate. And then cartilage cells are destroyed and replaced by bone on the diaphysis side. Okay, so on one side they're getting larger, and so they're going in one direction, and then they're being replaced by bone. Okay. Depending on the individual, the growth plate will close anywhere around, the textbook sort of numbers, 18 to 25. Sometimes This may occur younger. Sometimes it may occur older. In very rare instances, it may never occur in some people. And that's how you get giants. But let me give you, so here, let's just kind of zoom in on this growth plate, okay? So this is the epiphyseal end, so this is the end of the bone. Okay, so then here we have our here's the shaft would be down this way. Okay, so the shaft is somewhere down there. Okay, so this is the epiphysis. So if we zoomed in on this epiphyseal plate, we're going to see there's 4 different zones. The one that is closest to the end, to the epiphysis, is called the zone of resting cartilage. And it is doing just that. Basically, its job is simply to attach the epiphysis to the rest of the bone. Okay. Underneath that, we have the zone of proliferating cartilage, and as its name implies, it is proliferating, meaning it is dividing. So this is the area of dividing cartilage cells. Okay. Underneath that is another area of cells, or layer of cells. These are maturing cells, so these are no longer dividing. Okay, so they're just maturing. And then underneath that, we have the zone of calcified cartilage. So this cartilage is starting to turn into bone. Okay, so here it's starting to turn into bone. Okay. So basically, as the cells are dividing this way, so as they're dividing toward the end, right behind them comes the bone, and it's trying to catch up to that. And at some point, it will, right? The proliferating cartilage will no longer proliferate, and the calcified cartilage will simply overtake it until it's all turned to bone and you stop growing. Now, that's how bones get longer. However, bones also get wider. So your bones, and this again should be obvious, but like the width of a child's arm is much, much smaller than the width of your arm, even the bone, right? So basically this is what's going on. So if you take a look at this image here, you have a blood vessel, and so here's the periosteum, right? So you have osteoblasts in the periosteum, again, those cells that are building bone, and you have a blood vessel. So if you kind of look at this image just to the right, you'll notice that those osteoblasts are basically building bone, so it's wrapping around that blood vessel, right? And then what's going to end up happening is that periosteum fuses. So you still have some osteoblasts on the inside, but then there it is on the outside as well. Okay, so basically here are the osteoblasts, and they're going to keep building bone in, and that's how we actually get our concentric lamellae, right? And you can kind of see that process is going to repeat itself and basically kind of engulf that other blood vessel right here. Okay? And so that's basically going on along the periphery, on the outer parts of the bone. So that's what's going to allow bone to actually get wider. Right? And mind you, we're zoomed in super much. So I mean, that's why you don't feel all these ridges and bumps on your bones, right? It feels overall smooth to you. However, basically this is what's occurring. That's how your bones are getting wider. Right? Different things are going to affect your bone growth. So, for example, obviously calcium amounts. Right? We saw rickets in the previous topic in the integumentary system, right? So calcium is going to be really important. If you can't absorb calcium or you don't have enough in your diet, you can't make enough bone. Same thing is true for phosphorus, right? You have calcium phosphate as one of those minerals making up that hydroxyapatite, so you have to have both. Vitamin C is actually very important in collagen formation. And again, you have to have collagen for proper bone formation. If you don't, you will have very brittle bones, and we'll see how the extreme of that in a little bit. You also need specific hormones to drive this process. So you need to have something called an insulin-like growth factors. These will promote cell division at the epiphyseal plate. Oops, back one. You need human growth hormone. That's what HGH is human growth hormone, as well as your different thyroid hormones and insulin. All of these are going to be key in allowing proper bone growth. We'll talk more about these hormones when we get into Bio 202. Your different sex steroids at puberty will also influence how your bones grow. It's pretty obvious, but guys tend to have narrower hips than females, right? Females tend to have wider hips, narrower shoulders. Guys tend to have heavier shoulders. Guys tend to have more rugged jaw lines. All those think of all those things that kind of, your typical male-female differences. Those are all going to be influenced by the sex steroids. What you're looking at here is a condition called acromegaly. So this individual that you're seeing here is suffering from something called acromegaly. What ends up happening is sometimes individuals keep secreting very large amounts of human growth hormone. And what you can see here, so that it doesn't subside, right? After that spurt of growth, there's something that keeps signaling bones to grow. Now, unfortunately, the epiphyseal plate has already closed. So bones can't actually get longer. So what they end up trying to do is they go thicker, right? So here's the individual, I forget, they're like in their early teens here. And you can see how this person, as they're aging, you can particularly see that their brow ridge becomes more prominent. They have this much more prominent chin, like their lips, their nose becomes much broader, things like that. Because basically these bones can't get larger, so they're kind of growing out. I'm sorry, they can't get longer, so they're growing out. Okay. Sometimes if individuals lack estrogen receptors, they go pretty tall. Basically, estrogen is what's responsible for the closure of the growth plate. Both males and females produce estrogen. Females obviously produce a lot more estrogen than males. So basically, that's usually why females are shorter than males, because obviously more estrogen, that growth plate closes a little bit earlier in development. Excuse me. Okay. There's actually there's a gentleman who lived back again, like late 1800s, early 1900s, before antibiotics were created. His name, if you ever want to look him up, his name is Robert Wadlow, and he actually had a tumor on his pituitary that prevented him from ever going through puberty. So he never produced those high enough hormones to close his growth plate, so he kept growing. He actually never stopped growing until his death. So he's the largest recorded individual to ever have lived.